Okay, initially, a radioactive sample contains of 1 exponent 6 nuclei. The half-life of the sample is half-life. Okay, calculate the number of nuclei present after 0.5 half-life. That means another half of the half-life. Okay, so how to do these questions? Okay, so here, of course, we are going to use this exponential law of radioactive decay. Okay, the first formula, n equal to n naught exponent negative lambda t. Lambda is decay constant. Yeah. Well, actually, there are two ways to do these questions. Okay, we can use this one exponential law, or the other one we can use this formula. N equal to half to the power of number of half-life, and then n naught is the initial nuclei. Okay, n naught. Okay, so there are two ways. I'm going to show both ways and see whether we can get the same result or not. Okay, so here we have look at this one. Here we have the sample initially. Initially, yeah, that means at 0 second. At 0 initially at 0 second, this sample has this amount of nuclei. So this is the n naught. This is the number of nuclei at 0 second. Okay, n naught, and then it has the half-life. Okay, this is the half-life. And then find the number of nuclei present. That means find the final number of nuclei after this time taken. So this is the at time equal to 0.5 half-life. Yeah, so this is the total time taken. So want to find the final number of nuclei, yeah, after this time. So how are we going to do this question? So we're going to use this formula, n equal to n naught exponent negative lambda t. Okay, so we're going to use that formula, n equal to n naught exponent negative lambda t. Okay, so we know that the decay constant lambda is, what is the lambda? Decay constant lambda. Lambda is ln 2 over half-life. Yeah. So we know lambda is ln 2 over half-life. Ln 2 over half-life. Okay. So the half-life is half-life itself. So okay, I can substitute this lambda with ln 2 over half-life. Okay, so substitute it, n equal to n naught exponent. Wait. This n naught also given 1 exponent 6. So maybe I can substitute that one also. The value 1 exponent 6. Okay, 1 exponent 6, and then exponent negative. Wait a second. Put it a little bit below here so that better. Okay, put it a little bit further. Okay, so my lambda is ln 2 over. My lambda is ln 2 over half-life. My lambda, I substitute my lambda with ln 2 over half-life, and then my time taken. My time taken is 0.5 half-life. So I substitute with 0.5 half-life for my time taken. Okay. So find the n at this time. So here I can cancel my half-life. You can see that I can cancel my half-life. And then I can calculate. Actually, I can calculate. So 1 exponent 6 and then exponent negative. So this one is ln 2 multiply with 0.5. ln 2 multiply 0.5. So I get this one is 0.34 0.34 657 0.34 657 maybe add one more 6574 6574 okay 0.34 6574 okay. So let's calculate I have this exponent. Okay, where is my exponent? Okay, to the power of negative 0.346574. Okay, and then multiply by this one exponent 6, one exponent 6, and the answer is my answer is 7.071 exponent 35 exponent 5 radioactive nuclei or unstable nuclei remaining. So I have this amount of nuclei remaining. Okay, at 0 second it is 1 exponent 6. So after this 0.5 half-life, I have 7.071 exponent 5 nuclei remaining. That's the answer. Okay, so that's the first method. That is the first method. How about the second method, which just now I suggest using this one, n equal to half to the power of n, and then n naught. Because this is by the concept of half-life, number of time half-life. Every time of half-life, the number of nuclei decrease by half, decrease by half. So if you have 2 times half-life, it becomes half and half. So it's 1/4. So number of half-life is the power of the half there, power of the half. So if twice half-life, then it's 1/2 to the power of 2. That means it's twice half, half times half. So it's 1/4 lah, 1/4 of the initial number of nuclei. So I use this method. Okay, I want to write it down first over here. The second method, see whether I can get the same result. So n equal to half to the power of number of times half-life and naught, where n is the number of half-life, okay, number of half-life. So how to get this number of half-life? Okay, how to get this number of half-life? Very easy. To get the number of half-life is you just take the total time. You just take the total time or time taken divide by half-life. Understand? So you just take the total time taken, divide by half-life, and then you can get the number of half-life. So my total time taken is this one. This is the time total. This is the total time taken. Total time. This is the total time taken. So I can that one is the total time taken. So use that one. My total time taken is 0.5 half-life. Divide by half-life. So it is half. So that it is 0.5. Is 0.5. So this one you put power of 0.5 and equal to half to the power of 0.5. Okay, and what about n naught? N naught is, okay, wait, This one go a little bit over here. Okay, now n naught, just put the value 1 exponent 6. 1 exponent 6. 1 exponent 6. Let me, okay, 1 exponent 6. And now calculate. Yeah, calculate. See whether I can get the same answer. So half to the power of 0.5. Okay, to the power of 0.5, and then okay, and then multiply by 1 exponent 6. I'll multiply 1 exponent 6. I got the answer 0.071. 0.071 exponent 35. Oh, exponent 5 also. Exponent 5 nuclei remaining. So you see the answer is the same. Either the first method or second method, the answer is still the same. Okay. So both method accepted, both method accepted, but normally we use the first method because it is quicker. It is quicker, and normally in the list of formula also provide this formula. Also provide this formula. So you normally we use the first method. Okay. So but I just want to tell you that the second method also viable, can be done, get the same answer. Okay. So there are two ways to do these questions. Okay, that's all. Okay, bye. See you in the next video.